So until now we have discussed scattering wave amplitude, and now we are going to discuss diffraction conditions. And before that, I will try to brush up what a reciprocal lattice vector is. Okay, so um, so we have seen that the local electron number density n of r is equal to, in 3 dimensions, is equal to summation over ng, summation over g ng e raised to I g dot r. Okay, and g is the reciprocal lattice vector. Now we have to find this g. Okay, now we have b1 b2 b3. Okay, so we have g is equal to v1 b1 plus v2 v2 plus v3 b3. v1 v2 b3 are constants, integers, and sorry integers, and b1 b2 b3 are primitive reciprocal lattice vectors. They are primitive vectors in reciprocal lattice. The primitive vectors in reciprocal lattice, just like a1 a2 a3 in direct lattice, they are the primitive vectors of direct lattice. Okay, just like a1 a2 a3 are primitive vectors of direct lattice, b1 b2 b3 are primitive vectors of reciprocal lattice. So if we have what we have in hand is information about the direct lattice. Now we have to find a g or reciprocal lattice vector from the information we have in hand. That's information about the direct lattice. So we have to have some relations between direct lattice and reciprocal lattice using these primitive vectors. So that is what we have here. Okay, I will explain how we have arrived here. Okay, now if we have a direct lattice like this, and its lattice vectors are these three primitive vectors. This is a1, this is a2, and this is a3. Okay, then I try to find a equation for its volume of this unit cell. I try to find a equation for volume. So volume is equal to area into its height. Okay, it's lower area into its height. So V is equal to area. We can write. So what about height? Height is the if you take these two planes, height is the interplanar distance d. Okay, and we can substitute height as d. So volume is given by V is equal to A into D, and so 1 by D is equal to A by V, and we know 1 by D HKL is a length of the vector that takes you from a plane in direct lattice to the reciprocal lattice point. So we can write P1 is equal to A2 cross A3 divided by A1 dot A2 cross A3. So the denominator shows the volume element, and the numerator shows the area element, and we multiply a factor 2 pi with this, and it's a scaling factor. It doesn't do any harm to this equation. So in crystallography commonly we use 2 pi also in this equation. What we have got here is b1 is equal to 2 pi into a2 cross a3 divided by a1 dot a2 cross a3, and b2 is given by 2 pi into a3 cross a1 divided by these are the volume terms, and these are the area terms. So we have obtained three reciprocal primitive lattice vectors that are corresponding to that are components in a reciprocal lattice vector G. Okay, they are components in a G. They are primitive vectors in a G. Okay, and from this equation we can find a relation bi dot aj is equal to 2 pi into delta ij, and this shows if b1 dot a1 is equal to 2 pi, and if b1 dot a2 is equal to 0. I hope you can understand that from these relations. Okay, now okay, we have let's take this as a direct lattice plane, and this as a this as it's a corresponding reciprocal lattice. So if we have a okay, let's draw a reciprocal lattice vector G. Okay, reciprocal lattice vector G takes you from a identical point in reciprocal space to another identical point in reciprocal space. So corresponding to this G, we have some planes here. We know this dots in reciprocal space is denoted is a notation denoting some planes in direct lattice. So to corresponding that to that those we have corresponding to those G, we have some planes in direct lattice, and they can be related by translation vectors T. Okay, in direct lattice, translation vector T takes you from a point um, uh, that connects two similar points, or take you from one point to another point that are very similar. So here also we now no, I hope that was clear to you. And there is, if one vector G is here in the reciprocal lattice, that obeys a translation operator also. That obeys a translation operator also, because it takes you from one plane to another plane, and here it takes you from, and direct lattice you take it take you from one plane to another plane. So now we have this equation. N of r is equal to summation over G Ng e raised to I G dot r, and that gives the electron number density. That gives the electron number density. Now I am applying a translation operator T into that. Now, okay, it's N of r is a Fourier. It's a unpacking, or the the local electron density is expressed as a sum of some sine and cosine terms, or this is the Fourier expression of the local electron density. Now I am applying a translation operator T into that local electron density. Okay, now applying a translation operator T into that N of r, what I get is this. Okay, I will get e raised to I G r plus T, and when I split it, this is what I get. Okay, summation over G Ng e raised to I G dot r dot T e raised to I G dot T. Now we have to find what e raised to I G of T is. Now to find e raised to I G dot T, they have claimed that it is equal to 1. Let's find it, how it is equal to 1. So we know what G is. That is V1 V1 plus B2 V2 plus V3 V3, and V1 V2 V3 are primitive vectors of reciprocal space. Okay, and we know what T is. That's U1 A1 plus U2 A2 plus U3 A3, and A1 A2 A3 are primitive vectors of real space. And doing this calculation, we know that if I and j are the same, then you will get 2 pi, and if we have to multiply all these terms together, and the only terms that survives are those terms that have same indexes. B1 A1, if we multiply B1 with A1, that term survives, and B1 with A2, it will not survive. Okay, so only surviving terms are, so B1 into A1 gives 2 pi, and correspondingly here we have 2 pi, here we have 2 pi. We have 3 terms that are surviving. So I get the 2 pi in common. I put it outside the bracket and write u1 v1 plus u2 v2 plus u3 v3. Okay. So e raised to I 2 pi into a integer. Okay. E raised to I 2 pi into an integer is equal to 1. So from cos 2 pi plus I sin 2 pi expansion. Since this is an integer, we have to cos 2 pi is equal to 1, and so is e raised to I 0 t equal to 1. Now, so we have an invariance uh, from the previous page. We had an equation like this, e raised to I g dot t, and when this previous page we have an equation like this, m n n of r plus t is equal to ng exponential I g dot r into e raised to I 0 t, and we find out that this is 1, so we have an invariance. So we have found this is equal to 1. So here we have understood the while applying a translation operator to electron density, the Fourier transform of that representation also doesn't vary. It also follows, the Fourier transform also follows that properties while undergoing a translation operator T. Okay. Now to sum up, I have drawn this diagram. So this is just a direct lattice, and it have two lattices associated with it. One is the crystal lattice, then a real lattice, and its reciprocal lattice. And it's if we allow some X-rays to fall into this lattice and take the diffraction pattern, we find that this diffraction pattern maps its reciprocal lattice. We allow some X-rays to fall into this crystal lattice and analyze its diffraction pattern. We find its its diffraction pattern maps its reciprocal lattice. Diffraction pattern maps its reciprocal lattice. Now I have explained to you this in detail in the previous parts. So now let's compare direct lattice and reciprocal lattice. Direct lattice will have a dimension L, and reciprocal lattice have a dimension L inverse. Now a reciprocal lattice is a lattice in the Fourier space associated with the crystal. Okay. So I am repeating this point again and again because it is a very key concept to understand this chapter. Okay. So reciprocal lattice is a lattice in Fourier space associated with the crystal. So a crystal is in direct lattice, and if we take that crystal into a Fourier space using a Fourier transform, what we obtain is a reciprocal lattice. That is a key concept. And now we are going to understand diffraction conditions. Now in every explanation that are going to come in this chapter, because we are going to find different interpretations of 2d sin theta is equal to n lambda, or the Bragg's law. We are trying to find out different interpretations for Bragg's law. So now you have to keep in mind while approaching this problem. Okay. Now here we are going to find out the set of reciprocal lattice vectors G that determine the possible X-ray reflections. Okay. So here we are going to find out that Bragg's law. We are going to reinterpret that Bragg's law using Fourier transform. Okay. Now this is the same Bragg reflection that you have seen in the first part. Just inverted. In the first part it was like this. It's just a inverted representation, nothing more than that. Okay. Okay. Here we have a volume element dV, and this this denotes the first plane, this denotes the first plane, and this denotes the second plane. Okay, and incident beam incident on both planes, and it reflects. And incident beam is denoted by e raised to I k dot r. K is the wave vector, and k is the wave vector, and the outgoing wave is denoted by e raised to I k dash r, and k dash is the outgoing wave vector. Okay, now we have an angle phi here, and the path difference, the path difference between now we just like that Bragg's law, we have to find out uh, the path difference between these two uh, rays, the path difference between these two rays, to find out the diffraction conditions. Now we have here this vector is r, and so this path difference will be r sine phi, and this will also be this also phi, and this will also be r sine phi. So the path difference between those two points for the incident beam. Okay, for the incident beam, we have the figure like this. This is the incident beam, this is the outgoing beam, and we got this length as r sine phi. For the incident beam, the path difference is r sine phi. Now we have a well-known relation between the phase difference and path difference. Okay, we have a relation between phase difference and path difference that is given by phase difference is equal to 2 pi by lambda into path difference. So we have an incident beam and outgoing beam, and we have to find out the phase difference between these two beams. So we want to if we want to find out the phase difference, we have the path difference into 2 pi by lambda, that gives the phase difference. Now the phase difference is given by the difference in phase angle, or the phase difference is given by 2 pi by lambda into r sine phi, and which is equivalent to k dot r. Okay, 2 pi by lambda. Okay, 2 pi by lambda is the wave vector k, and k dot r is equal to 2 pi k dot r is equal to 2 pi by lambda into r sine phi. Okay. Now for the this is all these discussions was for the incident beam. Now for the diffracted wave, we have minus k dash dot r. Okay, if we have k dot r here for the diffracted wave or the reflected wave, we have minus k dash dot r. Okay, now we have to find the total phase difference, or the total difference in phase angle. So it will be difference between these two, and it will be k minus k dash dot r. Okay, the total difference in phase. Now we from the previous page, we have a volume element here, and here we have r sin theta, here we have r sin theta, and we have found out that the total phase angle phase difference between this wave and this wave is given by k minus k dash. So the total phase difference is k minus k dash dot r, and so the phase factor between these are we represented the incident wave as equals to I k dot r. So the phase the difference between phase factor between these two incident and outgoing wave can be represented by the difference can be represented by e raised to I k minus k dash dot r relative to the okay. So we have a volume element dv and origin O. So we have a reflection from here and from here. So the difference in phase factor between these two incident and outgoing wave will be e raised to I k minus k dash dot r. Okay, that's the first concept. Then we have seen earlier that the amplitude of the scattered wave, or the scattered wave amplitude, is proportional to n of r. Scattered, we know that we found out scattered wave amplitude ng is, we have a the scattered wave amplitude ng is equal to inverse volume into integral over cell n of r into e raised to minus I 0 t r. So it have a direct proportionality with n of r. So amplitude, scattered wave amplitude have a proportionality with local electron concentration. So we have a difference in phase angle, then we have a proportionality with the scattered wave amplitude. Okay, we are going to find out the final expression for scattered wave amplitude by incorporating all those things that we have discussed from part 1. Now we have phase difference, phase factor difference, e raised to I k minus k dot r, k dash dot r, and proportionality with the local electron concentration. And the next factor will be that volume element. And I show you that we have a volume element from which this reflection occurs. So it will have some electrons, and it will also have some, or the local n of r will be dependent on the volume that we are taking. So we have to take incorporate, if you want to find out the final scattering wave amplitude, we must incorporate the volume element also into our equation. So using that, we get the total amplitude of the reflected wave, or the total amplitude of the scattered wave will be proportional to volume element, the local electron density, and the difference in phase factor. And by incorporating all that, we get the final equation for scattered wave amplitude f is equal to integral over dv n of r, the local electron density, and e raised to minus I delta k dot r. Delta k represents the change in the wave vector k minus k dash, and this represents the scattering amplitude. Now we can represent this change in delta k vectorially. So we have two vectors, and its difference vector is denoted by delta k. Okay, k plus delta k is equal to k dash. Now as of now we have taken the incident vector as k and a reflected vector as k dash as two different vectors. Okay, now if it's a elastic scattering, k will be equal to k dash, both will be same vectors. So now in Bragg scattering from a periodic lattice, any allowed delta k must be equal to some reciprocal lattice vector g. So now we are going to connect this delta k with, we have a change in wave vector, that's delta k. Okay, and this delta k should be equal to g if our diffraction pattern to be obtained. So that's the next important concept that we are going to see in this chapter. So we have a reciprocal lattice, and each point in this reciprocal lattice represents a set of planes in direct lattice. So a vector that connects two reciprocal lattice points should be that vector that is equivalent to the change in wave vectors in the direct lattice. In order for a diffraction condition to be satisfied, the change in wave vector should be equal to the reciprocal lattice vector g. So any g's in reciprocal lattice vectors doesn't satisfy the diffraction condition. The diffraction condition is satisfied when that g is reciprocal vector g is equal to the change in wave vector delta k. Okay, now the incorporating. Now we are trying to we have this equation for scattering amplitude, and we have n of r here. Okay, now we are incorporating n of r also into in terms of Fourier components into this equation. So we have earlier found out n of r is equal to summation over g ng raised to I ig dot r. So now incorporating that into this equation, we will get summation over g integral dv ng raised to I g minus delta k dot r. And if we have a g minus delta k here, okay, and if g and I told you that g and delta k must be same or equal if diffraction condition to be satisfied, and if g and delta k are equal, we get this term as 1, and so when delta k is equal to g, see, all this term goes, it will become 1, and integral over 1 dv into ng. So while integrating, we will get volume v, and we will get f is equal to the scattered wave amplitude. Now if f, or the total scattered wave amplitude, is negligibly small when delta k differs significantly from any g, okay, so if delta k and g are not same, they are not equal, then the scattered wave amplitude will be very low or negligibly small. What does that mean? Okay, that means no diffraction occurs. That means diffraction condition is not satisfied, and to satisfy a diffraction condition, we need delta k equal to g. And when delta k equal to g, we will obtain a high scattering wave amplitude. That means diffraction occurs there. Only because of that, we get a high scattering wave amplitude. And if they are not equal, diffraction condition is not satisfied, so diffraction doesn't happen. So we have negligibly small scattering wave amplitude. Now let's consider for an elastic scattering, we have I told you earlier that the magnitude of both k and k dash, the incident and reflected beams will be same. So I can square that, k square equal to k dash square. Now we have found delta k is equal to g. So I can we have k minus k dash is equal to g. So we can club these two and write k plus g is equal to k dash. All these are vectors, okay. K plus g is equal to k dash, and so we can write this relation from, and this, take it as 1, take it as 2, and for k dash substitute k plus g, sorry, for k substitute both k and k dash are equal, so we can and k dash is equal to k plus g, and so for k I can replace k plus g. So I replace the using this equation, I replace this equation. I can rewrite it as k square plus 2kg plus g square equal to k dash square. Okay, this equation becomes this. Now have k is equal to k dash. I can cancel these two, and I can write 2kg plus 2kg plus g square equal to 0, and this is a diffraction condition. Okay, and I can, if g is a reciprocal lattice vector, and minus g will also be a reciprocal lattice vector, so I can write 2kg is equal to g square. So this is another form of 2d sin theta is equal to n lambda over the Bragg's condition. So I told you earlier that this will be interpreting the Bragg's law in different forms. So we have found out another form, 2kg is equal to g square or the diffraction condition. So this is the same as the Bragg's condition using wave vector and vector k and reciprocal lattice vector g. Now we are going to see Laues equations. Laues equations is also another form of interpreting Bragg's law. Okay, so we have the diffraction condition, delta K is equal to G, and I'm now here taking a scalar product with respect to A1, A2, A3 are the primitive vectors in direct lattice. So I'm taking a scalar product of A with the delta K. So delta K is equal to G, that is equivalent to taking a scalar product of A with the G, and G, as we know, G is equal to V1 B1 plus V2 V3 V2 plus V3 P3, and as per this equation we know, I'm substituting this instead of G, I am substituting this equation. But we know only similar indices B1 and B1 into A1 will give B1 dot A1 B1 dot A1 will give 2 pi, and other any other combinations will be equal to 0. So I take A1 into B1 into 2 pi. We will get A1 into B1 into 2 pi, so this will be equal to 2 pi into V1. Okay, that's what we have written here. Okay, and similarly doing for A2, we will get A2 dot delta K is equal to 2 pi V2, A3 dot delta K is equal to 2 pi V3. Now these three equations are called Laues equations. Okay, these three equations are called Laues equations, and they are another way of representing delta K is equal to G. And we can give geometrical interpretations to Laues equations. So here we see a vector that's rotating about an axis. So the vector is delta K, and it rotates about the direction A1. It represents delta K rotating about A1. So for the first Laues equation, A1 dot delta K is equal to 2 pi V1 can be represented as a cone, and it can be viewed as a the vector delta K rotating about A1, and so for all three Laues equations we can imagine a cone like this, delta K about A2, delta K about A3, and the delta K should be equal to G. So so for delta K is equal to G to be satisfied, all those Laues equations must be satisfied simultaneously. So in order to satisfy them simultaneously, we have to imagine three cones intersecting. Here we have shown two cones intersecting, and if we imagine one more cone into this arrangement, and those the G, or reciprocal lattice vector G, which is equal to delta K, should be inside the intersection region of all these three cones corresponding to Laues equations. We can interpret it in another way using evolved constructions, and that will be discussed in the next class.